Girolami to the floor. I'll hand over.
Well, good morning, and thanks very much for the invitation to come and open up this workshop for the day. This is the second time I've actually spoken at a Cantab Capital event in as many weeks, in fact. The first talk was quite technical. This talk will not be technical. What I will be doing is asking the question, is data-centric engineering, this is a phrase that is starting to enter into the scientific and technical vocabulary. Is it like AI? Is it like digital twins? Is it like big data? Is it like, I'm trying to think, what are the other hype things that are around at the moment? Well, you know most of them. Is this just another piece of hype? Or in fact, is someone trying to play a joke on us? You know, the emperor is walking about with no clothes. Or indeed, is there some substance in here that will form an organizing principle for all of the engineering sciences and the mathematical sciences, the statistical and the computing sciences? And the way that I'm going to do that is present some work that we have been doing at the Alan Turing Institute. And just to very briefly tell you about the Alan Turing Institute, is that it is the National Institute for Data Science within the UK, and it is comprised of a number of university partners, one of which, of course, is Cambridge. So, what is data-centric engineering? Well, I'm going to argue that it is an emerging discipline, that it isn't a subject of hype, although those that are over-enthusiastic and government ministers will indeed hype it up, that it is a substantial contribution to the engineering sciences that requires, as I said, the pulling together of a number of areas of the mathematical, the statistical, the computing, and the physical sciences. So it is most certainly an emerging discipline. I mean, so much so that Cambridge University Press have, in August this year, launched a new scholarly journal called Data-Centric Engineering. And the whole idea of what we're trying to do at the Alan Turing Institute is define this emerging discipline and establish capacity, right? That engineers that understand what data is, understand information, understand, to some extent, the mathematics of information within it and data. And that, of course, is going to require training and education. And as far as the research and the translation of that is concerned, we want to have global reach and influence. Now, I invariably start a talk by putting up a picture of Lord Kelvin. There are three reasons for that. One is he was the great Victorian natural philosopher and technologist as well, and certainly deserves not to be forgotten. But secondly, he was Professor of Natural Philosophy at the University of Glasgow for over half a century, which of course is where I came from. So Kelvin very much looms large at Gilmore Hill at the University of Glasgow, even now. And finally, he actually comes from my hometown in Largs in the west coast of Ayrshire in Scotland. But the key thing that the reason that I think Kelvin is important for this discussion around whatever data-centric engineering happens to be, is that he was, as I said, a great natural philosopher, but a great experimentalist as well. And his argument was that if you want to understand something, you need to be able to observe it and to measure it. And if you cannot measure something, you cannot improve it. And I think that the skeptics amongst us could say data-centric engineering. Engineering has been data-centric since Kelvin and before that, and I would completely agree. Data and information and evidence from a statistical perspective is completely central to the engineering sciences, to the engineering professions. However, there is something different that I'll talk about. So a quick plug, this is the Cambridge University Press new journal on data-centric engineering, and it would be great to talk to you about this. But let me start by describing some of the things that we've been doing at Turing in establishing this whole notion of data-centric engineering. The first thing is that the Lloyd's Register Foundation, they commissioned a technology foresight review in 2014 on what the impact of big data would be. So big data was at peak hype in around about 2014. Interestingly, we don't tend to talk about big data anymore now. But in 2014, they commissioned this report on what would be the impact, or what will be the impact of big data on engineering. And the outcome of that was a proposal to government that a program of research be established at the Alan Turing Institute, which at that point was still just something that was being discussed at government level, to establish this program. And so there was 10 million invested by the Lloyd's Register Foundation to establish this program on what became known as data-centric engineering. So I took over as the director, and the very first thing that I did was I established a challenge-led format. And we were going to have 3 grand challenges, right? 3 visionary challenges that were really going to push and motivate engineering practice and consequently the engineering sciences that underpins that. And these 3 grand challenges would be the concentration points for everything that the program was going to do. All research would be focused on these 3 grand challenges. All translational work, all high technology readiness level activity with companies would all be focused on these 3 grand challenges. And what were the 3, or what still are the 3 grand challenges? Well, the first one was, how can we improve and enhance the resilience or the robustness of our critical infrastructure, such as transportation networks across the nation, water supply, agriculture. How can we ensure that that will be, its resilience to those shocks, to those 1 in 10,000 year events that are going to have catastrophic consequences? How can we build that in to our critical infrastructure, that infrastructure that keeps our socioeconomic systems going? So that was the first grand challenge. The second one was that if we want to be able to make what are essentially going to be complex systems, right, at a national and an international level, more resilient and more robust to shocks, we need to be able to monitor these complex systems. Now, here it's called engineering systems, but in many ways they are socio-technical systems. How do we monitor them for those rare events that are going to have high consequences? And then the final one was that if we really are in a data-rich age, and that's debatable. But if we are, then how can a data-driven perspective be embedded into the design process that feeds through into the manufacturing, into the operation, into the decommissioning, and so on, and make the design process far more efficient and also meet the requirements for resilience and robustness and so forth. So those were the 3 grand challenges. We recruited a number of senior academics, all holding chairs at various universities, to lead these 3 grand challenges. And under those 3 grand challenges were a number of group leaders, some of which are seconded from Cambridge to the Alan Turing Institute, where they are, as the name suggests, leading groups and building capability, applying for grants, bringing in PhDs and postdocs, and pushing forward their various research agendas. And the program has grown quite substantially in tandem with the way that the Alan Turing Institute has grown. And you can see that we pretty much cover all of from the south right up to Scotland, although the most important part of Scotland still hasn't quite managed to get into the Turing ecosystem yet. But there has been tremendous growth, and in each one of these universities there is at least one group leader, so one faculty member who is seconded to the data-centric engineering program, and they are given seed corn funding, and then I have a chat with them and tell them that I want to see 4 times that amount of funding coming back from them. And we've been very successful in getting grants from EPSERC and actually leveraging that initial 10 million, as I'll talk about later. On the international scale, again, the program, we have a number of collaborative research programs from as far as the University of Sydney in New South Wales, and then a very substantial program at the University of Western Australia. Very interesting work here with Shell, which I'll mention just in a moment. And then various other places in North America, mainly in Canada as well. So there is national and global reach. I mentioned that we received 10 million from the Lloyd's Register Foundation to establish this program. This clock isn't working. No, it's not. So, how long have we got left? Yeah, okay. So it's how long have we been talking for? About 20 minutes? Yeah. So the key thing here is that we received 10 million. Now, when most of us academics receive funding, we spend it down. Primarily because that's the financial model of the university institutions. Here what we have done is we have grown this program. And from that 10 million initial budget, we now have an operating budget of 40 million. And that is comprised of program grants from the research councils. It's comprised of research grants from the likes of Shell, Arup, the National Air Traffic Service, and so on. Quite a diverse portfolio of funding, although the majority of it is coming from the research councils. So this is quite important. And again, this is important in terms of establishing capability and doing something that really is not restricted just to the national scale, but to the international scale. You're mathematicians here, so I guess some of you will know Terry Rough Paths from Oxford. So Terry is now, he is associated with the data-centric engineering program, and some of his work that's derived from his fundamental work on rough paths is now being used in solutions to monitor or to detect hazardous human behavior in building sites, or here what you see is in one of these vertical axis wind turbines. And this is work with and funded by the Health and Safety Executive. We have another one, and this again is work with the Whittle Laboratory here at Cambridge, where they have seconded a number of people to the programme, where we are looking at, I'm going to use the terrible phrase, digital twins. So mathematical models coupled to physical reality via data that's coming from the actual gas turbines. And what we're looking at there is better design of blades and compressors. And then another project which is very high profile, this is with the Lord Mayor of London's office, the Greater London Authority, and this follows on from the maxim of Kelvin, which is to say if you want to improve something, you need to be able to measure it. And for those of you who haven't been asleep for the past 10 years will be aware of the crisis in terms of the quality of air within London. And one of the key issues is how do we measure the quality of air? And one of the things that we are now doing is actually looking at this. You know, if we want to be able to improve the quality, we need to be able to improve the way that we monitor and measure it so that we can assess just exactly what that quality happens to be. And the mathematical and the statistical challenges associated with this are bringing CFD experts, are bringing urban analysts together, are bringing statisticians together, and are bringing chemists as well, who are designing certain types of portable sensors to better get coverage and improve the inferences of what sort of particulate levels there are within the capital. So this is all work that is mediated by the fact that we have data and amounts of data that previously we didn't have. I'm going to just give you a few little technical examples to show you just some of the things that we're doing, little snapshots. So Shell operate the world's largest floating liquid natural gas facility off the west coast of Australia. These are monster ships. They're the largest, so Prelude is the largest floating vessel that has ever been constructed and operates. And on that, there is the drilling capability for gas. And in addition to that, all of the processing plant, rather than being on shore, is actually on the drilling vessel. So everything is done on the vessel. And what that means is that from a business perspective, they now have a much more efficient way of both drilling, refining, and then delivering the product to their customers. One of the challenges that they face is that every day they have to make a decision. Do we start an offload of the liquid natural gas onto a customer vessel that's drawn up, or do we not? If we don't, we lose 50 million. If we do, and we have to abort because of the local Met Ocean conditions, we lose 50 million and someone probably gets sacked for making a bad decision. And so they take in a huge number of pieces of information to help them make the load, no load, offload, no offload decision. And one of the things that they are interested in that particular part of the world is the development of solitons that can impact on the actual structure. So remember, this ship, right, is floating, but it's tethered to the ocean floor. And so any high energy and high amplitude soliton waves that impact on these stay cables can have catastrophic effects in terms of the stability of the ship when offload is occurring. And so we were asked, they wanted a way of assessing from the data that they were measuring at the local, so the density of the ocean, right, around about the ship, and from that infer, what is the likelihood of certain solitons of certain amplitudes developing. And what they wanted was, not a yes, a soliton's going to appear, or no, everything's fine. They actually wanted some probabilistic representation of what was the likelihood, given the conditions that we've measured, that there may well be some developments. And so a group of the data-centric engineering program worked on this, and what we then did is we developed an iPad application that the engineers could use on the ship. Clearly, we weren't showing them these third-order PDEs, but we used a metaphor. Given the data, here is the likelihood of certain risks occurring. And so we went out to Perth in Western Australia and we pitched this to them. And this is now actually being used as part of the protocols to decide when a load or an offload should take place or not. We've got another program. So I should say that the data-centric engineering program operates across all of the engineering disciplines: civil, geotechnical, structural, marine, maritime, electrical, mechanical. Across all of them, we have a large group of mathematicians of various flavors, from stochastic geometers to PDE people and statisticians of every flavor as well. And this is just one group that have been working on this kind of new emerging area called probabilistic numerics. And that seems to be going reasonably well. Where did I put the pointer? That's here. So that's all going fine. This is one project with St Thomas's Hospital in London, in the large cardiac unit, where they are now generating patient data, right, in terms of videos of the whole heart. So this is a particularly damaged heart, as well as certain electrocardio measurements as well. And what we have been looking at is, how do you synthesize data like that? Right? So data that can't be embedded in some sort of vector space, like a video, or can't be in any kind of natural way without sitting down and thinking about it, and inform a multi-physics model, a multi-chemistry model, such as this here. So again, this is work which was funded by the foundation and subsequently by the British Heart Foundation, and that's ongoing work. So the reach of data-centric engineering goes way beyond what we would consider as the sort of natural areas of engineering. Many minutes? 10? 5? 15 to go? Oh, plenty. This is another one, a bit more classical engineering, where we're using a hydrocyclone to separate different types of fluids. And again, the key here is that we would like to have a coupling between a model and the actual data that we can observe, we can measure from the system, and use that to quantify notions of uncertainty in predictions of the purity of the the liquids that are separated. Probably the poster boy project that we have at the moment is a 3D printed stainless steel bridge, a pedestrian bridge that's going to span one of the, it's going to be a walkway across one of the waterways in Amsterdam. The technology of 3D printing a structure like this is quite phenomenal. And in terms of the opportunities that it brings to structural engineers, it means that they can think about designs that hitherto they've never been able to think about previously. You know, beautiful curves like this and so on. However, what is not known are the material properties, are the structural properties, right, of stainless steel that is printed in 3D. And for that, we have pulled together a large team of structural engineers, materials engineers, mathematicians that have been working on the modeling of composite materials, mathematicians that have been working on inverse problems where you have a very complex unknown field. So in this case here, the distributed stress tensor, and have very, very little data in comparison to the number of unknowns that we have in this case, as I said, a complete field. The very first thing we needed to do was make sure that this was going to be safe and satisfy the regulators, that this wasn't going to fall down. And so a number of structural engineers have been doing all of that sort of testing. But we also have, as I said, materials engineers who are now starting to tease apart some of the structural properties which are completely different from rolled steel. And this now, you know, brings us into a completely new environment, which is extremely exciting. So we have bridges, you know, which are almost, you know, look like something that came out of outer space. And then we have the bridges that we use every day, we rely on every day, and if they break down, then our journey into London is usually, you know, really devastated. And yet, these are extremely interesting structures, and what we're now starting to see are bridges that, when they're constructed, networks of, in this case, fiber optic sensors are embedded within the concrete structure, and that allows us to obtain data about the operation of this asset in real time. And so one of the things that we're doing, along with Network Rail and Microsoft, is delivering the very first, for the UK anyway, remotely monitored structural asset because of this data. And so decisions can be made remotely and therefore much more efficiently and quickly, especially in terms of safety critical situations. And if I was talking to a government minister, I would say that yes, we're building a digital twin that is going to be AI enabled, using big data from this bridge, because this is now an intelligent bridge. But the reality is, the reality is that, you know, we are using, you know, the finite element methods. We are now, you know, looking at ways of integrating data into the finite element methods and so on, and looking at the statistical characterizations longitudinally of how these structures actually perform. So, all very exciting. I mentioned the 3D bridge. I'm not going to go into the details, but you know, some of the material aspects, you know, make this a really very interesting inverse problem, and also a very interesting design problem as well. In fact, I was on the phone today to some colleagues in the engineering department here at Cambridge, just about how do we infer what the overall strain fields are on this structure when it's in operation. And it is a really very challenging inverse problem, as it happens. So we're doing all of that. The metallurgical analysis shows that, well, there's great anisotropy and directionality, as you would expect. But again, that then changes all of the design rules, and this brings us into this whole brave new world as far as the use of this particular material is concerned. So, I'm going to close by saying that I would argue that a data-centric view on engineering at the professional level and at the level of the businesses that, or the business sectors that all engineering operates in, is being transformed, and it's being transformed by data. I'll give you one example. A company in Bath makes valves, right? Not the most high-tech or glamorous of things. A valve that closes, oil or what have you in a pipeline on or off. That's what they do. And so when Shell or BP or someone else, Conoco, open up a new facility, they order 10,000 valves from this company. And business is good. Some time ago, they started to experiment in putting little sensors in their valves to see if the valves were closing efficiently and so forth, just as a self-diagnostic. They then started putting more sophisticated valves in that actually allowed them to measure, just how much flow was going through the valve, and what was the efficiency of the cutoff, and what was the constitution of the multi-phase flow that was going through it, and so on. And immediately they realized that this data that they were generating from their valves was actually extremely valuable. And so their business model has now been completely transformed from constructing valves to one of offering a service where they will manage a certain part of the process plant. Rolls-Royce is the same. They don't sell gas turbines. They sell thrust by the hour. And they can do that because of the data that they obtain from their operating turbines. So across all of the engineering sectors, business models are being changed. And as far as the engineering sciences are concerned, data is making, or is asking questions that previously have not been asked. And the requirement for mathematicians, again, of all hues, right, statisticians of all hues, working with engineers to understand the implications that data is going to have on the underlying sciences, and I've just given you some examples here, has never before been more important and more exciting. At Turing, we have over 140 PhD researchers, faculty, research fellows, PhD students, postdocs, engineers seconded from industry, working on these sorts of challenges at the fundamental research level, and also pushing right through to practice within the engineering sectors. So my closing argument is that data-centric engineering is definitely something of substance. There is real science. There is real multidisciplinary work that needs to be done. There is real commercial impact. So yes, there is hype. No, I don't think it's a hoax. And I'm arguing that it's providing and presenting fantastic opportunities for mathematicians, for statisticians, computer science scientists, and engineering scientists to really push forward the agenda of engineering. So I'll close there. And if there's any violent disagreement, feel free to shout.
That was fascinating and so nice to hear more about sort of engineering real-world application. We have time for questions, if anyone would like to ask any.
Well, good. Could I ask, I was intrigued by your bridge. I mean, the 3D printing of stainless steel, I mean, if you have a sort of 3D printer that you just buy from Argos or whatever, it'll basically sort of build up the object
Yeah.
sort of passing through scanning.
Yeah.
Can you do that with steel, or is it done by sort of cutting out from a solid?
No, it's not. I mean, because that's subtractive. So this is additive. Now, typically you would have a powder, and you would then sinter that up, right? Here, for something of that scale, then they have been developing technology based on wire arc additive manufacturing. So you basically have, think of it as a welding rod, right? That is then, a robot then just traces out the surface of the material in 3D. And so it lays up. So it starts off solid, it's then sintered.
So it's kind of additive, then you just have like little jets that are kind of putting this material onto what you've already built.
Exactly. Yeah. So it's layered. Yeah. So it's different from the sort of the smaller scale stuff.
Yeah.
What do you start with? You start with one little kind of simple.
That's exactly what you start off with, a little nib, and then off it goes. Now, the challenges here are the control of, because this is not done in a thermally, an environment that is well controlled, and the control of the quality of the way the sintering is actually being driven is still very primitive. And so what we are starting to see, so you start to see these sorts of things, right? And these are faults, these are macro scale occlusions, right? And they're randomly distributed, right? So you basically have this stochastic layer of faults in the manufacturing process, which overlays the bulk material properties. And we still don't know, the materials work is now starting to try and understand what the grain structure is like. So at the micro level, but at the macro level, and this is very interesting, because from an inverse problem, if we want to estimate, well, what is the strain field? Well, we can't assume that the whole thing is going to be deterministic. It's now completely stochastic. And so that opens up a whole new, we've got people who have been working in homogenization theory, looking at what are the types of stochastic PDEs that we would require at multiple levels to describe, these sorts of inherent faults which are going to impact the structural characteristics. Sorry, I haven't heard any hype about neural networks. What's a neural network? Okay. Yeah.
They might be somewhere in the background, but I just noticed it's one of the first things that pop up in a presentation.
I didn't mention anything about neural networks in here.
Exactly, yeah, so that's one surprise.
Okay, so I mean okay, full disclosure, deep learning, and this is being filmed, so my colleagues in Cambridge who are big AI aficionados will hear this. The technology hasn't changed for over 30 years. You still have this layered, non-linear cascade of transformations. What has changed? Two things: the amount of data. I mean, I've put loads of photographs of my cats onto Facebook, right? And compute power. And those two things have certainly made an impact for certain classes of problems. we still don't know what it is, and there are mathematicians, serious mathematicians, that are now trying to understand what's going on. Most of the things that we're looking at here are associated with safety. So the last thing you're going to do is put technology in that you have no idea what's going on. So, so I have basically said we're not putting neural networks into this 3D printed work. We're going to, we're going to do we're getting serious proper mathematics in. Now, let me temper that statement by saying that in inverse problems, the use of these deep networks does empirically seem to be doing something in terms of, defining a regularization, function, or in a Bayesian perspective of inverse problems, some sort of prior. But that's very much at the, research end. So there is work going on there. But I try not to jump on more than one bandwagon at a time. So
Mark, you've described a number of beautiful problems. As you said yourself, the reason is very centric engineering, but it's also, what we call applied mathematics. I think you've quite convinced me that it's not another hype phrase, in the sense that, we're telling ministers there's this new thing called data-centric engineering rather than this old thing called applied mathematics. So I guess my question is, do you see, novel mathematical challenges, or sort of something that differentiates the applied mathematics that you're calling data-centric engineering? Is it high-dimensional sensor data, or what is it?
So first of all, I think that's a really great question, and I see data-centric engineering as a combination of the engineering sciences that are underpinned by applied mathematics, and maybe even pure mathematics in some senses as well. So it's wrong to say that this is just applied mathematics, because it's not just applied mathematics, right? Since I started working with geotechnical engineers, I realize just how complex the problems that they're working on is, and it's not amenable to being able to write down a nonlinear PDE to describe the phenomena. So, but applied mathematics is absolutely at the core of what is being done. And I think that these problems, this is a century-old PDE. This is nothing, but a couple of centuries. But I think there is definitely new mathematics that is being motivated by the sorts of challenges that. So for example, with this here, how do these are going to be? These are multi-level stochastic PDEs, and so the sort of work that people like Martin Heirer has been working on, where we can't just assume certain levels of regularity in the stochastic forcing. It's starting to provide a motivation for these things. Stochastic geometry. Wilfred Kendall has been looking at this because the design and the reality are two completely different things, and the geometry itself now has some sort of stochasticity because the process is highly dependent on a number of environmental factors, the control of robots that are interacting with each other. So I would say yes. There's new statistics, there's new mathematics, there's new computing science that's being motivated and being driven to really make advances in classes of problem like this.